Sounds great. All right, so the purpose of this one, kind of going to show, how to make modifications and run the case. You've seen where the properties are located. We'll briefly go through it again. Basically, look at that is how we generate the mesh with block mesh and snappy hex mesh, setting boundary conditions and initial conditions, which we haven't talked about yet. Those equations of state we'll look at again, some of the numerical schemes. Probes and other output types are going to be important here. And then also some post-processing and pair review. And then we'll go through the Kingery bull mesh wedge case, just so you can see another validation case. Okay. So we will start. Oh, one. Okay, so this case is slightly different than the version on GitHub. I've made some modifications that I wanted to kind of showcase. They're mostly for easier use of things. Specifically, yesterday I pushed them. Okay, so to start, we'll show that. So this is going to be our original domain. So we just have a cube, basically. And then, so running snappy hex mesh, we are basically looking to remove the wall. So I'm just going to show the ground and the internal mesh again. So basically what happened is we cut out this section of mesh, which basically just means now it can be treated as a wall, and you can have the flow stop there and respond accordingly. So this is what our mesh is going to be used. This is what our mesh is going to be. This region here, actually I'm going to clean this case. Okay. So this is going to be our original mesh. So original mesh, we just have a cube. So that was running block mesh. Then we're going to run snappy hex mesh. Actually, yeah. We're going to overwrite our old mesh. You can see it's very quick. We don't actually want to refine anything. We're just simply cutting out cells. And basically the reason we do that is because it matches exactly. So we're going to stop looking at those, and we can see that we have this wall that we've built. So now we have our mesh. We have basically an empty domain though. So we don't have any charge set or anything like that. So what we want to do is we want to set our fields. First, before we do that, we're going to look at the initial conditions, mostly just because we do actually have to read in these files to actually set them. So for Blast Foam, we require a couple fields. So we need mass, we need velocity, or sorry, we need density, we need velocity, and we need temperature. So when you do a single phase, that would be rho, P, and T. Again, so this .org file, basically, when you clean the case, it's not deleted, it's always kept. But if you're looking up, rho, and you have rho.org, it'll use that. Basically, it's used that way you can set fields. It'll create that new field. It'll have a certain number of cells. But if you clean it, it'll go away, and you don't have to worry about that anymore. For multi-phase, we're going to be using, we also need volume fraction. So if you do a two-phase simulation, so if you have like C4 and air, you just need whatever one you specify first. So in this phase properties file, we specify C4 first. So that means we need alpha.c4. If we specified air first, it would need to be air.c4. If you do more than two phases, you have to have all of them. You need alpha.all of them, just because of the way it works. Okay, so here we're going to be specifying our boundary conditions for the wall, for the outlets, and for the ground. So for volume fraction, it's really simple, zero gradient for all of them. We also have this include, etc. Constraint types here. Basically, this just, if we want to decompose the mesh before we run Snappy, it'll include all of these. Otherwise, walls will not be there, and when we actually try and use it, it'll complain. So that's why we have this file here. We also have our row.air, which we're going to be using a uniform field of about 1225. Again, zero gradient for everything. So if you want to have a fixed value at the outlet, you can do that. But this is where you specify them. And then also just generally for OpenFOAM, if you have a runtime selectable thing, so it could be boundary conditions, it could be activation model type, it could be equation of state type. If you type in something wrong here, it'll fail, but what it'll do is it'll give you a list of all the possible ones that you can use. So I will show you that in a minute when we actually start running stuff. So we need to specify the density of C4 as well. And then we need to specify the temperature everywhere. And then we need to specify the velocity everywhere. So here we're going to be using a slip velocity at the wall and a zero gradient at the outlet. Basically, this is the only one that's really used, or different than zero gradient, I should say. Yeah, pressure's the same. So this internal field here is what's going to be used as essentially your initial conditions. So obviously, setting a charge, we will not have a uniform volume fraction. And I don't know if anyone's concerned about this. So we also have a uniform value of rho, so density everywhere. So the important thing for setting a charge is not the density, it is the volume fraction. So if you have zero volume fraction, it means that your mass of C4 is actually going to be zero, just because it's volume fraction times density, which will give you your actual mass or actual density. So this will cancel out everywhere except where you actually want that charge to be set. So it's okay to have this set to the actual density everywhere. Okay, so these are initial conditions. These are pretty standard. Generally, outlets and walls are zero gradient for just about everything except for velocity. You can have some different boundary conditions for the pressure, like a wave transmissive boundary, which lets pressure waves exit a little bit better. Yeah, these are the general cases. Okay, so we have all of our initial conditions defined. So now what we want to do is we want to set our fields. So to do this, we need the set fields dict. So we're going to be using set refine fields because we're going to be using adaptive mesh refinement. So set fields is a standard utility in OpenFOAM. Basically, it takes this file, it looks at default values, it sets the entire field to that, and then it'll take these regions, which are defined here, and then set them to whatever value you want. So this is fine if you're going to be having a static mesh. There's no reason not to just use set fields. However, if you want to allow your mesh to unrefine, and you don't want to have a super fine mesh at all times in certain regions, you want it to be able to unrefine. So that's why we're going to be using the adaptive mesh refinement. And to really use that, we want to, refine these regions at the start and then let them go away, basically, as they become unnecessary. So what set-refined fields does is it takes these fields, which you can specify any number. So if you have a multi-phase simulation, you can specify, alpha.c4, alpha.tnt, alpha.air, all of them if you want, or just one of them. It'll look at these fields and say, okay, where do I have differences in this field? And then it'll refine that. This number of buffer layers, again, is the number of cells between levels. And then, so generally speaking, this default field values is not super critical for the regular set fields. However, for set refined fields, it is very important because basically it'll always, at the beginning of each iteration, it'll reset to this value. So if you don't have these included, it'll just basically continually expand where these things are set, which you probably don't want. So we have these default values set, and then we're going to specify our regions. Very similar to set fields. So all set refined fields, anything that you run with set refined fields will work with the standard set fields, not the reverse though. So we're going to be specifying a cylinder that we want to refine. So the way this works is for cylinders, we have to specify 2 points on a radius. For a sphere, we have to specify 1 point in a radius. Basically, this cylinder to cell, there's a couple different options. I'll show you those in a second. But they take variable parameters. So also new to set refined fields is this backup section. So as I mentioned with Snappy, if this region is too small, it might not see any cells, and therefore it might not refine anything, which is bad because it won't even start. So in order to get around that, what we do is we specify this backup region, which basically says, okay, if you don't find any cells in this area, make your search window a little bit bigger. So it'll expand it, it'll refine those cells, but it'll never actually set anything in those cells to finish. So you might specify, something that would equal 100 times the mass, but it will never actually use 100 times the mass. So that's not something that's a problem. So some other things here, we have this refine internal. So what this does is it says, okay, you have this sphere, or cylinder, sorry. Do you want to refine just the cells on the outside, or do you want to refine everything inside as well? So we want to refine everything inside. Basically, it'll allow everything to react a little bit faster. And then we're going to be refining up to level 5. So this basically just means, subdivide those cells 5 times. And within this region, we're going to be setting alpha.c4. All right, and then the last section, so this is new as of earlier this week, I believe. So we also have this option to refine patches. Well, any faces, really. So here we're going to be adding additional refinement to the walls. So to do this, we specify a patch to face. We're going to be refining the wall, and then we're going to be refining up to level 3. So we're going to be refining the faces. Basically, if you don't set this, it won't do anything. You can set values there, but it's not super critical. But this refined faces is what we really want. Okay, so I'm gonna, so to show you, you can set A, just really anything that is not correct, and it'll give you the list. Okay, so we're gonna do set refined fields. Okay, so we had a bad type there. So this prints out a list of everything you can use, or of that's type topo set source, which is what we're using there. So really for cells, you can use anything that is 2 cell. So this is, I don't actually know what that quality is, but topo to cell to cell. So this is like a cell set. Cylinder annulus, There's a ton of different stuff that you can use. And then if you're going to be setting faces or refining faces, you can use anything that says to face. The points are point sets, but you don't really ever need those. But yeah, so it doesn't matter what you're doing. You can basically, if you type in something wrong, it'll give you a list of everything you can use. OpenFOAM is very nice that way. It may not have drop downs, but it does give you a way to look at what is available. Okay, so let's make that correct. Actually, we're just going to do part of this. Okay, so we're just going to refine the charge for right now. Okay, so you can see it iterates. So it sets the fields, and then it'll select cells to refine, and it'll refine them, and then it'll do that all over again. So here what you can see is that it tried setting it with that original cylinder. However, it wasn't very big, so then it said, okay, well, I'm going to use the bigger one, and then it refined again. And after the second iteration, the cells are small enough where you can actually see that now. So it stopped using that backup region. Therefore, it's setting all these fields, and then eventually it reaches a point where it's refining 0 cells, sets the fields finally with whatever you had as your actual cell size or region values, and then it's done. Okay, so what this will give us so you can see, so this is just the wall patches and the ground patch, and you can see it refined, and you can see with the area where it refined. Something else we want to look at is the volume fraction. So this is basically going to be where cells were set. Oh. And actually, this is a good time to show everything else. Okay, so if you ever want to do any volume operations, you have to have the internal mesh turned on. So this mesh region will give you the boundaries as well as the internal mesh. And it'll also show you all the fields you have read in and all that stuff. So in order to, so if you want to use both the mesh, like the internal mesh to do something like a contour or a slice or something like that. However, you don't always want to see everything. There's this, so you can go to sources and then search, and this allows you to search things. And we want to use extract block. And basically what this does is it allows you to pick certain patches. Like we want to use the wall and the ground. And it'll allow us to actually just look at the things we've selected. So you can turn off one of these, it'll turn off the ground, but it allows you to look at it separately, but still use that original mesh without having to reload multiple files, which can be nice. Okay, so we now have this contour of volume fraction. So you can see this is what roughly the shape of our volume fraction looks like. So we have the cylinder here, which we're going to be using. And this is done using a contour. So this guy here, and basically you can specify what fields you want to contour as well as the value ranges. So yeah, you can specify 1 or 0, or shouldn't really change for this one. I guess it does a little bit. Yeah, so it interpolates values and then creates a contour from it. Okay, so this is what it looks like. All right, so yes, we saw the mesh without that wall refinement. This is what it looks like. So if we want to include wall refinement on this mesh, what we can do is we can add that patch back in, this patch to face, and then refine the faces up to level 3. And what this will do, did not work. There we go. So it'll select all those faces on the patch here. And we can refresh this, go back, and it'll add that additional